In this video, we're taking a look at angular momentum, and we're going to define what it is and calculate it for various particles and systems. Ultimately, the goal is to be able to solve momentum conservation problems, but for angular momentum. There are 6 fundamental laws of mechanics that we will have talked about by the time we're done with this, and those are Newton's laws, first, second, and third, and the conservation laws, which correspond to energy conservation, which we looked at previously, but now we've added in even in rotating systems, linear momentum, and angular momentum. And although linear and angular momentum are related, we think of them as separate quantities, unlike energy, where energy, even if it's rotational kinetic energy, is all part of the same thing. The way conservation of angular momentum works is that the angular momentum, capital L or sometimes lowercase l, of a system is constant under a certain set of circumstances. And if you looked at that video, what hopefully you saw is that the skater started out moving in a circular path or in a rotational motion, relatively slow, but then as they brought in their legs and arms, effectively changing their moment of inertia, they sped up. And that is an example of conservation of momentum. So in order to talk about conservation of angular momentum, we need to know what the angular momentum of something is. And we're going to start by talking about a single particle, usually given lowercase l. And this might seem a little strange unless you think of one object kind of spinning around. But hopefully when we put this all together, it'll make some sense. So if you have a particle moving with some linear momentum p in space, well, we can think of the distance from that, from some axis of rotation or origin point to that, and we define the moment or the angular momentum as r cross p, the r vector crossed with the momentum vector, or rp sine theta, or the part of r that is perpendicular to the momentum vector, or the part of momentum vector that's perpendicular to r and multiplied together. R is the position vector, and theta is the angle between those two when laid tail to tail. Kind of standard cross product stuff. The units are kilograms times meters squared per second. This is because we have momentum, which is a kilogram times a meter per second, multiplied by another meter. The angular momentum of a particle then has a direction because it is a vector, and that comes from the right-hand rule. When we talk about the right-hand rule for rotation, we think of if you curl your fingers around, your thumb points in the direction of the angular velocity. But since we are dealing with an angular momentum here, we're dealing with the same thing. We're dealing with the fingers pointing in the direction of the r vector, crossing into the direction of the velocity or momentum vector, and that will point in that direction. It turns out that because of this, it mirrors the direction of the angular velocity, right? So the direction of the angular momentum, your thumb, is actually the same direction as the angular velocity, which hopefully makes sense. And we can think of this in another way, right? So we have this particle, right? It is of mass m, shown there with some velocity at radius r. The linear momentum is 8 kilogram meters per second, and the direction is always changing. Whereas the angular momentum is rp sine theta, right, 24 kilogram meters squared per second, and the direction is out of the page because as you go around in the counterclockwise direction, your thumb points out at you. But what if the particle isn't circling the origin at all? For example, this particle. We could see where the origin is. We can think of the circular path we might want to take, but we can still calculate an angular momentum, right? As it moves, that r vector is changing. But does that change the angular momentum? And does it prevent it from having angular momentum? Right? If it does, then is L constant or changing? Well, the definition of L, of the angular momentum, is r cross p. And when you do a cross product, it's only the portion of the two vectors that are perpendicular to each other that matters. And since p is a constant, the linear momentum, even though r is changing, the part of it that is perpendicular to p is actually a constant, and therefore, right, And hopefully this makes sense. There's no net external torque on the system, so you're not going to change your angular velocity of the system. So the angular momentum is conserved, right? Can this moving particle have zero angular momentum? Sure. What if the origin, right, is such that the point we're measuring from is along that path? Well, then suddenly the angular momentum would be zero because the r vector, right, would always be zero, or at least the perpendicular part. So a particle doesn't have to move in a circle to have angular momentum, and that is the big idea. And angular momentum is not just like velocity, where it's a velocity multiplied by a mass and has some value regardless of where you measure it from. In this case, the origin matters. You can make it so that it's positive, that it's negative. You could make it so that it is zero just by moving the origin point. So just like all things rotation, the axis of rotation or the origin really matters. So what about a system of particles? Well, as you might imagine, if you have a bunch of objects that are moving with some angular momentum, right? Say this barbell with angular velocity of omega about that axis. Well, we can find the angular momentum of each individual particle, right? We know that L is r cross p, which should be L over 2 mv squared. But of course, v is just omega times L over 2, because that's the radius of that circle. And if we rearrange this, we get 1/4 mL squared omega. But of course, we can do that again, and we get these two values. But anytime we get an m times a distance squared, we should be thinking moment of inertia. And if we add these two together, right, both vectors pointing out of the page, so we can just add them, we get 3/4 mL squared omega. But as I said, I is just that value, right? mL squared is going to be the key for seeing a moment of inertia. So if the object is extended, we don't have 2-point particles, but we know it's a moment of inertia, we say that the moment of inertia times omega, or the thing having to do with mass in rotation multiplied by the velocity piece, is the angular momentum, right? So in this case, angular momentum is 3/4 mL squared, the moment of inertia, times omega. So how does this kind of compare to translational quantities? Well, in translational, we have linear momentum. In rotation, we have angular momentum, which you can get by multiplying, the r cross p vector. The momentum of a system is the sum of all the little bits, and it's equal to the mass times the velocity of the center of mass. In angular momentum, if you sum up all the pieces, you get I omega. And again, I is the mass equivalent for rotation, and omega is angular velocity. For impulse, that would be the sum of all the FDTs, gives us a change in momentum. We have the same basic idea here in rotation, that the sum of all the net torque impulses, if you want to say that, integral of tau, that's for torque, dt, equals the change in angular momentum. If there's no net external forces, the angular or the linear momentum is conserved. If there's no net external torques, the angular momentum is conserved. So we were able to calculate the magnitude of a single particle's angular momentum about a point, or a system's by adding up individual angular momentum, or by using I omega. The next piece is, how do we actually apply conservation of angular momentum? Using this idea that if there's no net external torques, then angular momentum should be conserved.